Right. So welcome back. So today we're going to demonstrate the practical section of the course on protein modeling, sequence alignment, structure prediction, and everything. So we're going to kickstart from sequence alignment. So this is our working directory. It's always our demo directory, which the folder we made available to us in the tutorial, so you can also repeat the exact same things I've done. Yeah, so today we're going to use cluster W on the command line to do sequence alignment of a set of sequences. So cluster W, check the course, you will see the installation. I think I already have it installed. So these are the files in the demo folder. So I'm going to we're going to look at this cluster.faster. So this is a file. So let's visualize it. So it's a file containing 3 sequences, seq1, seq2, and seq3. So multiple sequence alignment, as we mentioned, is a pairwise alignment for each of the residue or whatever nucleotide in our sequence across all the sequences. So it's a whole lot of work, especially if you have a lot of sequences. Yeah. So, but for now, we're just going to look at these 3 sequences. So we're just going to use a program which I've shown you during the course to do that. So we're going to use cluster W. Yeah. So if you run cluster W, it's going to say, oh, what do you want to do? I'll first of all say, oh, let me impute the sequence. I mean, the structure I want to, the file I want to do the sequence alignment on. And as I've shown you, the faster file must contain the 3 sequences, one after the other. The name, the sequence, and all that. So 1. Then it would ask me, what is the name? I'll say, okay, the name is cluster. I think the name is cluster.faster. Yeah. Good. Then it will ask me, what do I want to do? I'll say, oh, it's multiple alignment number 2. So it's an interactive section. So do complete multiple alignments now. So that's what I'm going to do. Number 1. It's going to ask me for the output file. Now, if I don't specify an output, the default is going to be cluster.aln. So, and that's what I'm going to do. I will specify an output so that the default remain cluster.ln. So I'll press enter. They will ask me for the guide tree. It finished the alignment already. It's going to ask me for the guide tree. Then I will say, okay, it's fine. Then it's done. So this is the sequence alignment. It's been able to do pairwise alignment for all the 3 sequences, as you can see here, where they align, and then where they differ. For example, seq1 and seq2 has valine here, while seq1 and seq3 has valine, seq2 has alanine. The same for here, 1 and 2 has alanine, seq3 has serine. So it highlights those differences. Okay, so we're going to end that, and then if we go back to our file again, let's visualize some of the cluster outputs. For example, cluster.dnd. Yeah. So cluster.dnd is actually a dendrogram that you can plot. So you just specify, the distance of each sequence from like a primary sequence. For example, taking seq1 as the central sequence, what are the distance of seq2 and seq3 from seq1? And you can see they are of the same distance here from seq1. Seq2 and seq3 are of the same distance. So yeah, because they only differ by a point mutation, both of them. So they're essentially very close neighbors of seq1. So that's exactly, so you can plot this. I don't want to show how to plot that, but if you have multiple sequences to make alignment, to do alignment, so first represent them like this, seq1, then list the sequences seq2, seq3 up to the number of seqs you want, 1000, whatever, and then you can run them. It can be computationally expensive, believe me, especially if you have a lot of seqs or sequences to align. Okay, So that is it for sequence alignment. So there are so many online web tools that can do this, but this is just a very simple way of doing sequence alignment for your for your for a list of sequences. Yeah, there are even more colorful way of doing that on some web servers, but I think I'll leave that out for you to find out. Okay, so the next thing we're going to look at is this. Let's look at some. I mentioned in the cost blast. So in blast, you're trying to find out. It's like sequence similarity. For example, if you have insulin that belongs to the human or that belongs to a rat or whatever, which other sequences across other species are similar to that sequence? Because you know that if they have similar primary sequence, most likely they are going to possess similar 3D structures. I mean, in terms of the protein or whatever have you. So we're going to use this sequence in the blast.in. I created a file blast.in. So let's look at it. Blast.in. So it has this sequence. So we're going to use it to perform a blast and see what it's going to return to us. So I'm going to copy it and I'll come here. So here you paste the faster sequences. So I'll just paste it. Then you can give a job title. You can also upload a file if you already have. For example, I already have this blast.in, although I need to maybe rename it blast.fast or whatever, then I can upload it here as a file. You can give the job title if you're interested, if you're doing multiple jobs and you want to keep track of it. Now you can also choose the method for the clustering. So clustered NR is always like one of the basic method to the clustering. Now what is important is you select the organism. For example, I want you to check sequence similarities in Homo sapiens, right? I want you to also check in sorry about that. Yeah. And also check in ratus. Then maybe just these two, right? So for these two organisms, I want you to check the other possible sequences that are similar to this in all these species. Yeah, because if we find those sequences, most likely we're going to find similar structures. So it's a way to also find homologs of protein in very, very many other species. So this is protein blast. And as we mentioned the last time during the lecture, blast P for protein, blast N for nucleotide, depending on the blast you want to do, blast X, T, blast N. So transcription from nucleotide to protein or from protein to nucleotide. So all those things are possible to be done in blast. So, and then when I'm done, I'll hit on blast. Then it will go on and do that. It usually doesn't take much time. In a few seconds, it will return the results to us. So it started returning the results, and then we can see that was actually an insulin peptide sequence. So we can see it's returning a lot of possible sequences it's seen belonging to primates. Obviously we put Homo sapiens there. There's some belonging to, and then belonging to primates, belonging to rats. And we can see a whole lot of even similar protein. For example, IGF-1A is not insulin, but it's a protein that is also similar to insulin. Then insulin-like growth factor 2 is not insulin, but it's a growth factor. And then on and on and on. So it will keep returning. So this is a way to, and then you can also look at their similarities. Yeah, you can look at similarities here. Percentage identity. So this is insulin pre-protein because this is an insulin sequence. Yes, obviously. So the insulin pre-protein has like 98% similarity. The insulin itself 99.09 because it's the insulin sequence. So it should have a very high similarity. Do you get? So these are things you do to retrieve other possible sequences, homologs, obviously, or analogs or autologs, whatever you want to call them. So this is how to do blast, and then there are a lot of other things that you can find out in blast. Now, I'm also going to demonstrate to us how can you fix missing residues in your protein? Now, remember the last time in the course we mentioned the issue of if you have a protein and you want to pre-process it and you want to fix missing residues in your protein, how do you go about doing that? Now there are a whole lot of tools to do that. If you're working on so many other softwares, Schrodinger, whatever, Chimera, there are many ways to fill in missing residues. We're just going to work on a very, very simple method to deal with that, which is, as I showed in the lecture, PDB Fixer is a standalone online tool that you can use. So if we call for help, it's going to tell us, oh, it needs some options. And then if you don't run with arguments, it will try to launch a web interface. So, but usually because my timeline here is not optimized to launch interface. I have issues with the graphics. It won't run. So we're going to specify the command verbosely and then we are going to run it. So I have a structure here, which is 9NSR. So it's the structure of a malaria plasmodium falciparum protein. So I'm going to it has some missing residues. Yeah, in fact, it's visualized somewhere here. So look at the structure here with a lot of missing residues. So I'm going to try and fix it. And then let's see. So I'm going to call PDB fixer, right? So then I'm going to call the protein 9NSR. Then I'm going to say, oh, add residues. Sorry, I think this is wrong. Add residues. Then I can also ask for variables so that it prints it out, clearly here. Yeah. And then I'll run it. Usually it just gives you an output named output.pdb or whatever the name is. So I've been say, oh, it's finding the missing residues, it's adding missing atoms, and on and on and on. And then when it's done, it will give us the output. Okay. So actually, so if you just want to, a very simple way to visualize what has happened is just to look at the difference between the two files. We will see residues that we are not in 9NSR that already have been added. You can still go further to visualize it in many of the visualizers like Chimera or what have you. Okay, so to find out the basic difference between the two files, whether our structures have been fixed, so we'll just do a simple manipulation. Yeah, the original structure, which is 9NSR, contains so many crystallographic information, which might not be necessary or useful for us, right? Okay, so we might just grab only the atom section. Grab atoms 9NSR into 9NSR clean. Then, sorry, I'm supposed to put a piping command. Piping arrow. So then I'll do the same thing for outputs. So now I have both clean for outputs and clean for 9NSR. So with this, I can now look at what are the basic difference between them. So we can see that the basic difference between the 9NSR clean and the output clean are some of the structure, some of the residues that were added during the fixing, as you can see here, right? So residue 35, 37. So you see the difference if you do a diff command minus S. So you can see the important residues that were added as part of the new structures that were not there in the original structure. So this is what it does. So you can go ahead and maybe visualize it in a visualizer, and then you're going to see that most of these missing chains has been filled up, right? Okay, so that's actually how to use a fix. So, but this I show you just a very basic way. There are many other ways to fix missing residues, especially if you're working in the context of many modeling softwares and a lot of them. So, what of mutation? I'll just show you how to do a simple mutation in Chimera X. So this is the same structure 9NSR that we just fixed now, but this is an unfixed structure, obviously. So I want to mutate a residue, which is serine 248. It's here. So I will ask for a background color of white to make it better. So see the residue I want to mutate, it's highlighted already in green. So maybe I will also change the color. Atoms and bonds, make it cyan by heteroatoms. So this is residue I want to mutate. So I'll call for the command line interface. Oh, I ran the command already some a few days ago. So swapper is the command in Chimera X. So swap this residue 248. As you can see, if I hover over it, it's 248. Swap it to threonine or swap it to phenylalanine or whatever. In fact, let's try phenylalanine. And then you see, I've mutated it. So this has become the new residue. Now, it's from the Drunken library. Now, there are a few more commands that you can use. So first of all, try to, what do I say? It's to optimize the torsion angle, exactly, torsion angle of this new residue to avoid clashes. Because, for example, this phenylalanine obviously might be having clashes with like this um tyrosine residues, as you can see here, or maybe even this arginine residue. So this is just a very simple way to mutate your structure. If you're using PyMol, you're using whatever tool is available to you, there are very many ways of mutating your structure. So, but this is just a very simple way. Camera X, I've used it, and then you can also use a lot of other tools. Now, what if we want to model the structure of our protein, the 3D structure of our protein? Oh, it was not available. I can't find it in PDB. What do we do? So let's first of all look at Swiss admin. Sorry, Swiss model, obviously. So, and then we're going to use the structure that is available here. I have a structure here in AlphaFold.faster. Yeah, so I have a sequence in AlphaFold.faster. So it's a sequence of a protein. The protein we've just been working on 9NSR. So we want to try and do a homology model on it. So even though the structure exists, we just want to use it to serve as an example. So this is Swiss model. So what do? We're going to paste this sequence here. And then the first thing to do is to search for templates. Right. So this structure does not exist theoretically, right? So we need to find other homologs, maybe similar structures from maybe nearby species, close species, that's already available, and use that as the template to build the structure of this molecule. And you can give a name or whatever if you have so many other projects you're working on to avoid confusion. So the first thing is to search for templates. And then when you've done searching for templates and you got a template, then you start modeling. So we're going to give it a few minutes and then let's see what it's going to give us. As you can see here, it's running BLAST, so obviously it's going to do sequence alignment with a whole lot of sequences available in its database before it will be able to give us an output. All right, so we have a whole lot of structure here. Let's say, for example, we have from Plasmodium vivax, a very similar species. Oh, it's available up to 73.39 sequence identity. In fact, because this structure is already available on the PDB, it even found a structure that is 100% identical. Obviously, that's why it found this, but we are going to assume it's not available. So we're just going to use one of the structure, which is 5HN7 from Plasmodium vivax. So now that we've chosen one, so usually it's sequence identity that is one of the most important because you want to use a structure or a homologue that is very, very close so that the confidence in the model you are building will be very high, right? So you can now start building the model. So that is the next step. So that was so fast. We are done building our model. So this is our first model built on the template from the Plasmodium vivax. And then this is what it looks like. It's built from that template. So what is the next thing is to do? You can download the files, including the sequence, the structure, and everything. Okay. So to make a very good assessment of this model, we're going to look at some important um, just some important qualitative terms, such as you can see here, the predicted local similarity target. So this is actually how far is the prediction at each particular residue? How is it far from what it should be? As you can see, there is very, very low predictions at some residue, let's say residue 80. Yeah, you can see here, residues around 80 or around 200. So the prediction is very low, but at most other levels, there's high confidence in the prediction. And then you can see where the color, where there is blue, there is very, very high confidence. And where there is red, there is low confidence. You see, so most of the helixes, there's a high confidence in the prediction. But when we come across the loops, we lose confidence because of the high flexibility associated with the loops. And then you can also look at the average Q mean disco global. So it's 0.86. That is very, very high confidence. Up to 0.7 is really, really very good structure, predicted structure. So you can also look at the beta atom fluctuations, all atom fluctuations, solvation and torsion, and they are really looking very, very nice. So you can download this PDB format, model report, whatever. So, and then you are ready to use your structure for whatever modeling you want to use it for. Okay, so this is actually a very simple way to model, to perform homology modeling. Yeah, so, but we are going to move on into AlphaFold. We know the revolution is here. AlphaFold has changed the paradigm. You don't need to do homology model. From just the primary sequence, the 3D structure can be predicted. So now we are at the AlphaFold server. And then our job is going to be, first of all, paste our residues. Now we don't have any ligand, we don't have any ion, we don't have any DNA. So we are only going to predict the structure of our protein. So I'm going to just start running the job. So submit the job. So it's going to just take a little time. As you can see here, it's running. And then when it's out, we look at our structure, look at good criteria, quantitative measures that we can use to assess the quality of the predicted structures. And then, as I showed here, uh, if you have cofactors like magnesium ions, ATP, ADP, or whatever is available, you can also create the model of this protein together with these structures. So they are available and you can do them. And it's the same idea that we talked about in the course about co-folding. So if you have a ligand, you can actually model both the protein and the ligand together and calculate the binding affinity in one step. Yeah, I remember we said it's really pretty good, except that it's not amenable to throughput. So it's very, very low on throughput. So, but it's really a very nice idea. Okay, so we are done. We are going to open our prediction. So this is our protein in 3D, predicted protein in 3D. And then as you can see, the places that have blue, the blue color represent very high confidence. Then the other colors, for example, this loop at this terminal, this loop here at this terminal is actually showing red, like very, very poor. The fluctuation is crazy. So the algorithm is not very certain about the prediction. Yeah, but in many of the helixes, it's very confident. Then along some of the loops, the confidence drops, and then on and on and on. So that is actually what happens here. Now there are a few other things as what I just said now. Blue color, very high confidence, PLDDT, global confidence in the structure. And then if you have like cyan, it's between 90 and 70, which is still fine, but not very, very high. Then also at the residue level, the IPTM and the PTM are also, you see, very, very high, up to 0.93. So it's a pretty, like, very, very great structure. And as you can also see here, alignment of each residues against itself, it's fine. So when you check some of these metrics and they look really pretty good, then you can just download your prediction and then you can use it for your molecular modeling. Okay, so this is the end of the course, end of the demo on molecular modeling. So we've seen you can do all kinds of things: sequence alignments, you can do blasting, you can mutate your residue, you can fix your missing residues, you can do homology modeling. At the same time, you can also just use most of these AI tools to do structure prediction. Thank you for joining us. Have a nice day.